Okay, in this video we're going to take another look at binomial distributions, but let's assume that in this scenario we don't really need to know probabilities for specific outcomes, but now we want to change gears and we'd like to know what outcomes would be considered unusual. Um, Again, we need to remember that 95% of your data will fall within 2 standard deviations of the mean. So we need to be able to calculate the mean. We're going to use this formula here. The mean, or mu, is going to be equal to n times p. I'm including variance here simply because I think you might be asked that on my math lab question, but we don't need it for our purposes here to solve these problems. Then standard deviation is square root of n times p times q. My little note here that got chopped off was just reminding you that p and q are complements of each other, and usually you're going to be given n and p in your problem. Okay, if you can remember, variance is just the square of standard deviation, or standard deviation is just the square root of variance. So if you have one, you have the other. So that's not a far stretch there. But I want to remind you what we mean by the range rule of thumb. Values that are less than the mean minus 2 standard deviations are going to be unusual. So that mu minus 2 standard deviations is a critical value, and it's identifying the lower limit of what's normal. Values that are greater than the mean plus 2 standard deviations are considered unusual. So whatever that value is going to be that borderline separating the usual from the unusual on the high end of your curve. So that's just the wording for it. But basically, you just need to remember the values between mu minus 2 standard deviations and mu plus 2 standard deviations. Those are your usual values. So in other words, mu minus 2 standard deviations and mu plus 2 standard deviations are critical values, those borderline values that separate usual from unusual. And of course, as usual, the best way to kind of get this to sink in is to just do a couple examples. So we're going to look at our problem with that we did earlier in the binomial distribution where 60% of adults believe in the devil. We're going to calculate the mean. I'm not going to bother with the variance. And the standard deviation for a poll regarding adults who believe in the devil. Remember, we had 60% of adults believe in the devil in that problem. Would it be unusual to find only one person in a group of 5 who believed in the devil? That's one question we're going to answer, and that would be looking at that lower limit to see, does one fall inside or outside? Would it be unusual to find that all 5 people in a group of 5 believe in the devil? So that would be looking at that upper limit to see if 5 fell inside or outside the limit. So we're going to use these formulas that were at the top of the page. Mu is equal to n times p, and standard deviation is equal to the square root of n p times q. So we're going to plug in the information. Now remember, 5, we were looking at given 5 randomly selected adults. That's what your n is. And then p, 60% were believers in the devil. So I shouldn't say believers in the devil. They believed the devil in the devil. So we have 0.6 there, and so we come out with, on average, we could expect that in groups of 5, 3 out of the 5 would believe in the devil. On average, that's what that mu means. Our standard deviation works out to be a little bit more than 1. So if we think about this just roughly, that 2 standard deviations would be around 2 people. So if we said 3 plus and minus 2, that's kind of a range between 1 and 5. So we're kind of there on that borderline. But I don't want you to round just yet. So I just wanted you to make sense of what we're looking at in this distribution. We're not going to round. We're going to say 3 minus 2 times 1.095, and I just left 3 decimal places in here. So I get 0.82. That's our cutoff. Now that doesn't make sense in terms of a whole, it's not even a whole person, but it's going to make sense in our distribution. Then we have 3 plus 2 times 1.095, and we get 5.19, and again, you can't have 1900ths of a person, but it's going to make sense in our distribution. So when we draw our curve here, we've got our lower limit and we've got our upper limit. So we need to examine and answer these questions. Would it be unusual to find one person in 5 who believe in the devil? So 1 would fall just inside this range in here, and so that would not be unusual. 1 would be to the right of the 0.19, and it's in the usual range. It's not in the unusual. Okay, but 5 falls outside here. I'm sorry, inside here, so it's also in the usual range. So 1 and 5 are kind of on the high ends of things, but it's not unusual. What would be unusual is 0. That's way out here. That's going to be unusual. Now, I want you to keep in mind this is a really small distribution, so this really isn't the best example. I want to move on to something that makes a little more sense. Okay, a government agency has specialists who analyze the frequency of letters of the alphabet in an attempt to decipher intercepted messages. In standard Turkish text, a particular letter is used at a rate of 5.7%. We are going to find the mean and the standard deviation for the number of times this letter would appear in a typical page of 3,100 characters. So we want to find what's usual range, the number of times we should see this character in this page of document. So our mu is n times p, and we plug in, we find that on average in a document that has 3,100 characters, you would expect on average to see about 176.7 times to see this character. Our standard deviation, when we plug in our n, our p, and our q, as we have here, we come out with 12.9. Now, it's tempting to round, but don't round just yet. So we're going to take our mu plus and minus 2 times the standard deviation to come up with our lower limit and our upper limit of our range. And I'm sorry, I kind of had to squeeze everything in here, but we've got our lower limit and our upper limit. Within this range would be usual. Outside of that would be unusual. So in an intercepted message, a page of 3,100 characters is found to have the letter occurring 228 times. Is this unusual? So when we draw our curve, we can really clearly see it, that 203 is on the high end. That's our upper limit, and 228 is outside of that. So 228 times is unusual. And so if you were analyzing this document, you would say that's statistically significant. It's far more than what would be expected, so that document would, you'd want to scrutinize that a little more closely, that there's possibly a code embedded in there. So that's one use. We've got another problem here. Between 1974 and 2011, there were 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to random chance, meaning in the range of normal, or is 252 wins significantly high? It is. We need to find the mean and the standard deviation, and then we're going to use the range rule of thumb to find the value separating the numbers of wins that are significantly low from usual, and from usual from significantly high. So basically we just want to know, is 252 overtime wins in 460 games significantly high? So I've kind of written out here what we're doing. Again, we're using our range rule of thumb, mu plus or minus 2 times the standard deviation to find our critical value. So we need to find mu and our standard deviation. When we plug in 460 times 0.5, I got that 0.5 from common sense, that when you're flipping a coin, your chances of 50% heads, 50% tails. So that's where the 0.5 comes from. So that makes sense. Out of 460, you could expect 230 on average would be winning the coin toss, 230 on average losing the coin toss. So our standard deviation, it's not going to happen that 230 would win every time. It's not going to work out to be exactly 230, but give and take a little bit, we need to know how much is in that normal range, and that's where our standard deviation comes into play. So we calculate the standard deviation, so we know that it's going to be 230 times plus or minus 2 times our standard deviation of 10.7. And so that's what I've written down here to find our lower limit and our upper limit. I drew the curve and drew in where our lower limit, our critical value is for our lower limit, and our critical value for our upper limit. Now I didn't round these two things because you always want to go 1 decimal place, at least 1 decimal place more than what your x value is. So we're talking whole numbers here, so we'd go to the 10th place. So we're trying to evaluate, is 252 wins unusual? It's outside. It's just barely in that unusual range. So basically from this, we can identify that 252 wins is significantly high. So there must be that there's a psychological boost to winning the coin toss, but I think it's probably more likely that there's an advantage to being able to choose if you kick or if you receive. So, in a nutshell, winning the toss matters.